Gnanam Paramam Dheyam. Knowledge is supreme.
So, in the last lecture, I stated Dedekind-Artin's theorem, which says that the order of the Galois group is bounded by the degree of the field extension. So, to prove this, Dedekind proved it in a classical case, and Artin proved it in a little bit more general setup. So, I will first recall Artin's remarks, and then we will tie up, and at the end we will prove the Dedekind-Artin theorem. So, I am now preparing for Artin's a little bit more general proof. So, as usual, notation is L over K field extension. And assume finite. When I need really, then I will write down it is finite. But right now I don't need. So, if I take an automorphism sigma from L to L, K algebra automorphism, that means an element of the Galois group of L over K, that is sigma belongs to Gal L over K. Then that means if I just look at the multiplication, that means sigma L dot to L dot, this is a monoid homomorphism. Because it respects the multiplication, and obviously 0 goes to 0 because sigma is linear here, so 0 goes to 0. So, it will also induce L cross to L cross, a monoid homomorphism. More generally, I could consider see, ultimately we want to prove that there are as many elements as at most the number of elements in the Galois group are the degree of the field extension. So, somehow I have to relate linear independence and the elements of the Galois group. So, elements of the Galois group, they are monoid homomorphism. So, more generally I will consider, consider a little bit more general situation. So, I take a monoid, and I will denote monoid multiplicative. The notation will be multiplicative. And so called characters of M with values in a field, with values in L. That means what? That means monoid homomorphisms chi from M to L dot. Monoid homomorphisms. Such monoid homomorphisms are called characters of M with values in L. And the set of all monoid homomorphisms from M to L, I am denoted by chi M comma L. This is the set of all monoid homomorphisms from M to L dot, or characters from M2 with values in L. And think of, so this is a subset, so they are maps from M to L. So think of this as a subset of L power M. So L power m is not so good notation. So this is the set of all maps from m to L. So this all characters is a subset of maps from M to L, and this set has a structure. This is a vector space. This is a L vector space. Component wise scalar multiplication and component wise addition is a vector space structure on this set. That means you add point wise and scalar multiply also point wise. So therefore this set is a subset of this vector space. I want to prove that this set is linearly independent over L. That is what Artin's lemma. So this Artin's lemma states that chi ml is a linearly independent over L, linearly independent over L, a subset of this vector space L power n. Now, when do we say subset is linearly independent? When there is no linear relation. A linear relation is always a finite. So, that means no finitely many elements of this set satisfy a linear relation with coefficients in L. That is why O over L. So, let us prove this first. This is very simple. So, proof. So, suppose not. Suppose not. That means what? That means there are finitely many elements in chi ml and there is a linear relation among them with coefficients in L. But among all such relations, I am going to choose a relation which has a minimal length. So, this means choose L linear relation Z1 chi 1 plus Z2 chi 2 etc. up to Zn chi n, and suppose this is 0, where with Z1 to Zn are elements in L, coefficients are in L, and chi 1 to chi n, they are characters. They are elements of chi ml. They are characters from on M with values in L. And I want to choose n minimal. Choose a relation with an n minimal. So therefore, all these zi's are non-zero. So in particular, Z1 to Zn are non-zero. All are non-zero. Also note that n has to be at least 2 because no character is, so characters are always non-zero. Because it's a monoid homomorphism, so identity of the monoid is going to go to the identity of the monoid L dot, but identity of the monoid L dot is 1. So characters are always non-zero, and when the character is non-zero, any non-zero element times a character is also non-zero. So if at all there is a linear relation, it has to have at least length 2, and we have chosen the minimal one. All right. So now this linear relation means what? That means evaluated at every point of m it is 0. So, therefore, keep let us take two elements x and y in the monoid M, and let us remember that y I want to fix it, y is fixed element in M and x I am going to vary. So, when I evaluate this z1, chi1 etc., zn, chi-n, this evaluated at xy, x times y. xy are elements in M, M is a monoid, so product is also there, and this has to be 0 because we are assuming this linear relation is 0. So, evaluated at any element it is 0, but this is now what is this how is it defined, the linear relation? It goes inside. So, this is z1, chi1, xy etc., zn, chi-n, xy, this is 0. But this one is, because it is a monoid homomorphism, so this one is z1, chi1x, chi1y, because it is a monoid homomorphism, and so on. So, the last one is zn, chi-n, x, chi-n, y, this is 0. Now, this is in L, this is in L, this is in also in L, and this is 0 for all. Y is varying, but so this is y is varying and this is 0 for all y. So, therefore we get, I should have said x, keep x fixed and y varying. So, y is varying. So, therefore, from here you conclude that z1, chi1x, chi1 plus zn, chi-n x, chi-n, this is 0, because this evaluated at y is precisely the earlier one, and that is 0 for all y. Therefore, this linear relation we get with coefficients in L. And now I am going to produce a linear relation with a smaller length. So, now this one is 1 and the original one is this one, z1, chi1 etc. I want to cancel one term. So, I am going to multiply this equation by chi1x and let us see what happens. So, that means I want to multiply this original relation. So, I have to write on the next page. So, this original relation was this, and I want to multiply this relation throughout by chi1x, multiply. Then we will get z1, chi1x, chi1 plus z2, chi1x, chi2 etc., zn, chi1x, chi-n. This is still 0 because we have multiplied this equation by chi1x. And the new equation which I got, I will rewrite below this, that is z1, chi1x, chi1 plus z2, chi2x, chi1, chi2 plus zn, chi-nx, chi-n, this is 0. This is how we got this equation, this one. And now I want to cancel. So, I subtract. If I subtract this from this, what do I get? The first term get cancelled, that is how I multiplied. This get cancelled with this, and here what do you get? You get z1, z2, and what is the term? This chi1 minus chi2x. Chi1 minus chi2 x chi2 so on, zn chi1 minus chi-nx times chi n, and this is 0. But now all the terms, if the original relation is at least 2 elements, that means that all of them are chi 1 is not equal to chi 2 in particular. Because if they were equal, then I could simply add. If they were equal, then I will just club it with Z1 and minimize the relation. So we are assuming that all these chi 1 to chi n are all distinct characters. So I should have mentioned it in the beginning, like Z1 to Zn are non-zero, chi 1 to chi n are distinct. Since chi 1 to chi n are distinct, in particular this chi 1 is not equal to chi 2, and therefore at least one element they will differ. So there exists some x in M with chi 1 x is not equal to chi 2 x, and therefore this coefficient here is non-zero, because Z1 is an element in L which is non-zero. This is also an element in L which is non-zero, by we have chosen our x. So therefore this coefficient is definitely non-zero. So therefore I have a non-trivial relation whose length is less equal to n minus 1. So therefore it's not possible. It's a contradiction, because we have chosen a relation with the minimal length. So this proves the lemma. So this is not possible, since n is minimal. So that proves the assertion that chi, so we have proved, that this chi ml, this as a subset of L power m, this is linearly independent over L. All right. So now we will continue our proof of the now the proof. So let me recall what we are proving. So the theorem we are proving is the Dedekind-Artin what we are proving is L over K finite field extension then cardinality of Gall L over K is smaller or equal to the degree of the field extension. This is what we want to prove. So proof. All right. Let me recall. So the big vector space we are working here is L power m. L power m. Actually m is L I am taking. L dot. M is L with a multiplication of L. Okay, now this vector space obviously contains, there are maps from L to L and not arbitrary maps, but which preserves. These are all maps from L to L. And if I take the endomorphisms of the vector space L over K, that is a subset, because these are all maps from L to L and these are maps which are K linear maps. Okay. And among them, this odd K algebra L, this is a subset here, because when I say K algebra automorphisms, they are K linear automorphisms, and K linear automorphisms are endomorphisms. So therefore this inclusion is also clear, and this is our Galois group. So we are working here. and we are bothering about the cardinality. This is a big set. This is okay. Okay, now this endomorphisms, this one is actually what is apparent is it is a K vector space, because we can add two linear maps and multiply linear maps by scalars, and that becomes a vector space over K. Because K linear maps you can add pointwise, you can also add you can multiply scalar multiplication pointwise. That gives you a K vector space structure. But I want more, actually I want to say it is a L vector space. So I should tell you what is the scalar multiplication by L on that. So if I have a linear map F from L to L, which is K linear, this means F is an element here and Z is an element in L, then I should tell you what is Z times F. This should be again a linear map, K linear map from L to L, but that is you define on X is Z times Fx. This Fx is an element in L, Z is also element in L, so this is a multiplication in the field L. So with this definition, this scalar multiplication of L on this, note that this L, so therefore and L over K, this becomes L vector space. And then there is a subset here, that what we are interested in, Galois group of L over K. These are all automorphisms, K algebra automorphisms of L. Okay. Let us remember what is the dimension. Now I want to compute the dimension. So if I write dimension as a vector space over K of end, this I know what is the dimension. This dimension is same thing as L over K square. This is because you see, think of endomorphisms will correspond to the matrices. So matrix Mn K has dimension n square. So by that observation, dimension of these endomorphisms K precisely L over K square. Okay. So and what is the dimension of now as a vector space? So now I want to compute dimension of n K L as a vector space over L. What is the relation between these two dimensions? See, this is so recall here. I will write in a blue thing so you can do this thing. So here we have a K field, L field and vector space V I am considering L vector space. Suppose I have given this situation, and then V is also L vector space by restriction. And how do I compute what is the relation between dimension L over V and dimension V over K? What is whose dimension is more? As a vector space over L, the dimension will be less, and as a vector space over K, the dimension will be more. And what is how do you compute dimension? This is L over K. Multiply this by L over K and you get this. This is obvious because here the coefficients allowed are only in L and here coefficients allowed are in K. So each coefficient in L you convert into K by taking a basis of L over K, and therefore this dimension will be product of these two dimensions. That is obvious because take a basis L basis of V over take a L basis of V over L and take a basis of L over K and multiply this. So let me write it. So this formula can be proved very easily like this. So we have, you choose a basis of Vj L basis of V, J is varying in some set J, and take Zk K basis of L, K is varying in some set I, then you look at this Zk Vj, they are, and Kj varying in I cross J, then obviously check that this is a K basis of V. That means the dimension of V will be the cardinality of this, which is the product, and dimension of this is this one. So we get, so this formula is, therefore this is how we prove this formula. Now therefore what do I say? This dimension equal to this times the degree of L over K. Right? So we have proved this equality. Now if I want to compute this, I will just look at this extreme two thing and I will cancel one. So this proves that, I will write. So this proves that dimension of L dimension over L of these endomorphisms of L over K, this is same thing as L over K. This is what we have proved. And what do we want to prove? This dimension is L over K, and then we want to prove about this cardinality. This is a subset of this. So therefore, and we have proved the elements of this. See, what are these? See, this one is contained in chi. They are elements of the Galois group or the automorphisms of L over K. And then you can think of they are contained in L, chi, LL. These are the characters of L with values in L. Just restrict them to the multiplication map. So this is a subset here. So and then we have proved this subset is linearly independent over K over L. That is what we have proved. This subset is linearly independent over L. And so therefore the cardinality of this subset cannot be more than the dimension where it is contained. So this is therefore this subset cannot have more cardinality than the dimension of this as a L vector space, but that dimension is this. So that proves cardinality of the Galois group L over K is smaller or equal to the dimension which is this. That is what we wanted to prove. So we have proved that whenever we have a finite field extension, the cardinality of the Galois group cannot exceed the dimension of L over K. So this is very important step we have proved. That means whenever we consider finite field extensions, their Galois groups are always finite. And as I mentioned earlier, that this already proves that the Galois group of C over R is cardinality 2. Galois group of a finite field extension is also exactly equality here holds. That is what we have proved. So I will continue in the next lecture from here. Thank you.